Assalamualaikum dan salam sejahtera. Today we'll talk about a stable multivibrator circuit which is constructed by using 555 timer. We have R1, R2, C1 over here which will determine the frequency of oscillation of the stable multivibrator. F is equals to 1.44 over R1 plus 2R2 multiplied with C1. We have another capacitor over here, C2, which is connected to the control input. This one, for a stable multivibrator, the capacitor will be grounded. Your output is at pin 3, which is a square wave. For pin 4 and pin 8, it will be connected to the power supply VCC. Pin 6 and 2 is connected to the capacitor C1 and R2. 7, the discharge pin is between R1 and R2, and pin 1 is ground. So the internal circuitry of your 555 timer is shown in the red box over here. The external R1, R2, C1, C2. Okay. Now we are talking how does the square wave will be produced at the output pin at pin 3. Initially the output is 0, and at this moment your capacitor C1 over here is uncharged. So meaning that your VC1 is 0, and since this pin 2 over here and also pin 6 is connected to the capacitor, pin 2 will receive 0, and similarly pin 6 is also 0. So now we have two comparator CA and CB. For the lower comparator CB, the voltage here is VCC over 3, since we have three resistors over here, R, R and R, which is connected to the power supply. So the voltage here will be 1/3 of VCC, and this voltage is being compared with 0 volt at pin 2. Okay, the pin 2 over here. So meaning that your VCC over 3, which is at positive terminal, will be greater than 0 at negative terminal. So we said that V plus greater than V minus. So the output of comparator B will produce a logic 1. So your RS flip-flop will receive 1. And for the upper comparator over here, the voltage over here will be 2/3 of VCC. It is being compared with the input at pin 6, which is 0 volt, and this is 0 volt. So V minus will be greater than V plus. So comparator A will produce a 0 output to the reset pin. And since the RS flip-flop S receive 1, reset receive 0, your output Q will be 1. So previously it is 0 at the output. Now your output is plus VCC. And when your output is plus VCC, Q bar will be 0. Okay, Q bar is just opposite of output Q, and this Q bar is connected to the transistor over here. Since this is 0 volt and this is also ground, which is 0 volt, this transistor will be off. So now there is no path from this pin 7 to the ground. So at this moment you will be charging your capacitor C1 through this path from VCC through R1, R2. So your time constant tau will equals to R1 plus R2 multiplied with C1. Okay, now your capacitor is being charged from 0 until supposedly to be up to the maximum, which is VCC. But you'll see that the voltage at the capacitor won't reach the VCC, since we are comparing the voltage at the capacitor with pin 6. This is your VCC going to the pin 6, and we are comparing it at 2/3 of VCC actually. So at the moment, for the lower comparator, now the voltage here is still VCC over 3. We are comparing this voltage VCC over 3 with pin 2. Okay, now we are over here, somewhere over here. So meaning that V minus is greater than 1/3 of VCC. So we said that this comparator CB will be providing a output of 0, so set will receive 0. And for the upper comparator just now, I said that it is being compared with 2 VCC over 3. So this is voltage at this capacitor. Now we look at this moment when V plus greater than V minus, which is meaning that it is somewhere over here. Okay, when V plus greater than V minus, your upper comparator will produce logic 1. So your reset flip-flop RS R receive 1, set receive 0. So your output previously is high, now the output will be 0. Your Q will be 0 and Q bar will be 1. When Q bar is 1, meaning that this is higher potential than ground, your transistor here will be on. So there is a path from this node through pin 7, which is the discharge pin, to the ground. So at this moment, when your VCC is greater than 2/3 of VCC, the capacitor C1 will be discharging through this path through pin 7 to the ground, since this transistor is on. So what will happen? You will see that this capacitor will be discharging its value. Okay, and the path is through R2 to the ground, so your time constant tau will be R2 multiplied with C1. Now this is the graph for the capacitor C1. It is being charged from 0 to 2/3 of VCC. If it is greater than 2/3 of VCC, this capacitor will be discharging over here. Okay, but if we let the capacitor discharging, it will discharging all its voltage until 0. But we know that the lower comparator, the voltage across the capacitor will be compared with 1/3 of VCC, so it won't reach 0. So meaning that this voltage over here across the capacitor is being compared with only 1/3 of VCC. The moment the voltage across the capacitor, which is less than 1/3 of VCC, okay, your lower comparator over here, CB, okay, it is at this point. Okay, your voltage across capacitor is less than 1/3 VCC over here, so V plus will be greater than V minus, so meaning that set will receive 1. For the upper comparator, we are comparing with 2/3 of VCC, and at this moment the voltage over here is less than 2/3 of VCC, meaning that V minus is greater than V plus. Reset will receive 0, R0 set 1, your Q initially is 0, now it will be 1 again. So your Q bar will be 0, this transistor will off, since this is 0, this is ground, so this transistor will off. There is a path for there is no path from this node to the ground, so C will stop discharging the moment it is less than 1/3 of VCC. Now you are charging again your capacitor through R1 and R2. So this is the voltage across this capacitor C1. It will be charged again until 2/3 of VCC. You can read here about the circuit operation. What I have shown here is the output at pin 3 from 0 to VCC, and this is the output at pin 2 or pin 6, which is across the capacitor. During the output is high, the capacitor is being charged. Output is low, capacitor will be discharging, charging and discharging. So we have a square wave at the output. During high or TH, it is also called as a T mark or TM or T on. And for the when output is low, it is TL, sometimes it is called T space or TS or T off. Now we are going to find the time over here for the charging of the capacitor and T2 discharging of the capacitor. We are using the principle of capacitor being charged and discharged. This is the basic principle of relaxation oscillator, and the equation used is Vc at any time t will equals to Vc at initial value plus Vc at steady state minus Vc at 0 multiply with 1 minus e to the minus t over tau. Or if you simplify the equation, it will equals to Vc at infinity, which is steady state, plus Vc at 0 initial state minus Vc infinity steady state e to the minus t over tau. Tau is the time constant. Okay, now we look at the T1. It is being charged from 1/3 of VCC to 2/3 of VCC with tau equals to R1 plus R2 multiply with C1. And using this equation, VC at T1 is this voltage, 2/3 of VCC. VC0 is initial voltage. VC infinity, if we let this capacitor, it will reach the maximum, which is VCC, the steady state value. And plug in all this value into this equation and solve for tau 1. Okay, and we'll get that the tau will equal to, the T1 will equals to tau 1 natural log of 2. Tau 1 just now is over here. Natural log of 2 is 0.693. So you have your time taken for charging will be 0.693 R1 plus R2 C1. And similarly for the time low, we still use the same equation, only that the time constant now is tau 2, which is R2 C1, the discharging through R2. Use the same equation just now. We see at time 2, this is the time 2. So at time 2, it will reach VCC over 3 over here. Initial value, which is 2/3 of VCC, which is this one. And if we let the capacitor discharging, it will completely discharge until 0. This is the steady state value. Plug in all this into the above equation. Simplify the equation, find T2. Okay, we are taking natural log on both sides, this one. Okay, this is, I just simplify this. This is 1 equals to 2e minus T2 over tau 2. So I make it positive, so it will be T2 equals tau 2 natural log of 2. So T2 will be 0.693 R2 C1. So the time for one period T will equals T1 plus T2. We have found T1 and T2 just now. Combine that, so time for one period will be 0.63 R1 plus 2 R2 multiply with C1, or the frequency of oscillation, which is F, 1 over T, will simply 1 over 0.693 multiply with R1 plus 2 R2 multiply with C1, or it is 1.44 over R1 plus 2 R2 C2. Thank you.